the problem definition and less about how I'm going to approach it. It's active anti-resonance isolation system for engineering structures. So in this slide, I'll go from resonance to anti-resonance. So at resonance, an external vibration forces the system to vibrate at high amplitude when the forcing frequency is matching with the natural frequency. So even when the forcing frequency is away from the natural frequency, the system experiences vibration. So at anti-resonance, an additional system is introduced within the main system to generate a reactive force in opposite phase in real time based on the external forcing, such that a major part of the system experiences almost zero excitation. So like some part of the system mass and stiffness is varied so that the reactive force on the main system cancels the forcing on the main system. So that M mass, this mass will have a minima and main system will have a zero at that particular frequency. So main objective is to explore the ways of implementing in new ways of implementation in structural uh, engineering structures. And secondary objective is to explore the possibility of regeneration of energy with isolation. So this is the four ways how we can do it. So active tune mass damping, delayed resonator, then semi-active tune mass damper, and without using any additional mass, using feedback approaches. So I have spent some time on ABC. So D I'm yet to explore. So I'll go to the next slide, and next to that I'll explain these two. So in active tune mass damping, there is one actuator between main system and secondary system. So it replicates the effect of mass stiffness and damping of classical passive TMD based. It's all in real time sensing the displacement, velocity, or acceleration. So, so only this part comes because of the actuator. And these are stiffness and damping is fixed in active mode. While in semi-active, there is no actuator, but there is one variable stiffness and damping, which is so these two are not similar, but there is one delayed resonator where the effect of damping for the auxiliary mass system is varied such that the damping is zero. It acts as an undamped absorber, the auxiliary mass. So these are, as a simplicity, these are all uncoupled. So this I have to yet to explore more in detail. So two ways what I can think of is integrated MEMS or NIMS actuators and sensors with the structure, and other one is as a separate inserts in the composites or something. So in this, like what I found is it is applicable for aircraft wings, fuselage, automobile chassis. Then it is relatively expensive. Powering will be difficult. And there I see it everything green. I don't know why, but so, so powering I see it is easier when it is a discrete system in the structure. Then it can be replaceable. Then regeneration I can see that it is more achievable in that. So I'll go to both the approaches through schematics. So this is the using spring mass system. I'm trying to show the effect of MEMS or NEMS actuators. So like whenever there is a forcing, uh, there will be masses that will move, or we can say that the actuator will apply a force in opposite phase to cancel it. But we may not be able to do it in like the first go. So the error will reduce it gradually from support to the end. So second way which I could think of is as an insert. So this I have tried to show it as an insert with a spherical, like a spherical joints. But inside there is one permanent magnet that can oscillate in like three translation directions. So with three coils, one will be actuator coil, other one will be sensor coil, and one regeneration coil we can put there. So again, that gradually it will reduce the error, uh, and it can also prevent delamination in composites. So this has been implemented like NEMS actuators by NASA in reducing vibration in aircraft wings. Then like passive tune mass dampers have been there for like now centuries. Like YouTube filled with water is used to stabilize the ships, and a Taipei 101 in Taiwan uses a pendulum bob. So these are tune mass dampers. What we are trying to do is active, so there will be sensing and actuation in real time. So in aerospace structures, of course, then automobile industry, we can use it. Then structures, it's not very applicable, but that would be all. So I don't think I will be able to answer, but situations like
If last question and you have to answer now.
it was more like a dessert at the end. So
Exactly. Short
I
and
don't
sweet.
know how sweet it was, but
Short.
so less I have spent time that I was really afraid to whether it is foolish something to present like that.
It's just to get the monkey off your back. So good that in short duration you could go through so much of literature and get some idea after.
So structural dynamics class is also helping a lot.
Do you already know like which tools you will use to study that? Like software or programming your scripts or to understand the resonance of the structure that you will study? Right.
My basic plan is to understand the mathematics behind
Okay.
it. Like this uh, in tune mass damping itself in show. Like this I was not knowing, but in this when we solve the differential equation for x1 and x2 separately. So for x1 in numerator, it comes that lambda is equal to root of k2 by m, small m. So in order to make x1 0, we came to know that, okay, forcing frequency should be equal to root k2 by small m. So we have to vary m2, small m or k2, so that it should always match with forcing frequency. So that way I have to proceed. Then I have to find out like which of these are best suited for those two ideas. So like I'm still unable to get how it is happening. Delayed resonator. So I have approached 2, 3 professors. So waiting for their time. So, yes.